Hey guys, welcome back. And uh, first, if you know any Neal.fun copy starting to John.fun or Jack.fun, then, then can you comment to them? Like, I tried I tried doing I tried finding a new.fun site like winner.fun winner.fun, but the only thing I found was poop.fun, and they have no idea what this is. So, today we're going to do foxes. Finding foxes. Well, I thought it was called foxes. Imagine a little game. I give you a 3 by 3 word search and ask you to find the word fox. So, fox. Yeah, there's also fox. Yeah. The thing is, there is no guarantee of what exists in a word search I give you. Each grid is constructed randomly, with each square equally likely to contain an F over X. Given a randomly constructed 3 by 3 grid, what is the probability that you can find the thoughts? Oh, so about half. Well, content. Well, if we could look at every possible configuration of a geometry grid, we could just count how many have thoughts and how many do not. Because each square could have one of f4 reds, there are 9 squares. The total number of combinations is 3 to the power of 9, is 19,683. This is a very small number for computers with what? Just 838 of those grids have thoughts, and 41%. 4 by 4 grids. But what about a 4 by 4 grid? We can use the same method. Look at all possible grids and count how many have footers. 4 by 4 grid are 16 squares, so e to the power of 16, 43,046,721 possibilities. Not more, but still small for a computer world. There's out 34,755,800 grids have footers, around 81% this time. Oh, that's a big, that's a big up. That's that's almost twice. As the grid is larger, the probability of finding the foots gets higher. This makes sense because there are more letters we can use. Oh, oh, I'm gonna. Okay, I give up. I'm not going to get to the 0.0000 word grid. 5 by 5 grids. Oh, how about? Okay, well, how about a 5 by 5 grid? Now we start to run into trouble. There are 3 to the power of 25 is 847 quadrillion. 847 trillion, 847 billion 288,609,443. There's nearly 1 quadrillion. What do you mean? No, it's not. It's not even 1 trillion. They're not feasible to brute force by counting. Instead of looking at one square at a time, we can look at entire rows at a time. There are 3 to the power of 5, 243 grid rows, and 191 of these don't contain any foxes. If we construct a grid using 5 of these foxless rows, the only foxes to have to worry about are vertical and the diagonal. When adding a new row, we only need to consider the 2 rows above it and make sure we're not adding any foxes. This blends nicely with a technique called dynamic programming that lets us reduce the amount of checks from a quadrillion to around 20 million. The result is a 96.4% chance to find a fox in a random 5 by 5 grid. Uh, uh. Wait, is it a new rule? Yeah, I think it's the same rule. Sets by sets grids and beyond. There this number possible sets by sets grids. The problem is exponentially harder to solve as the grids are larger, but it's not lost. We can't always find the exact answer, but we can approximate it. See Monte Carlo sampling, we generate a random grid and check if we find the faults. We then do this over and over again millions of times. We keep track of how many photos we find, and with enough samples this converges to enough answer, to exact answer. I think the answer is often. Never mind. So more than more than 1,000 yes, less than 10 no. But for three-dimensional photos. Well, instead of looking at three by three, really we looked at a three by three cube of photos. Ah, this is confusing. It turns out there's a 92% chance of finding a photo in a three-dimensional cube. But why stop at three dimensions? Four-dimensional photos. Bring out the 4 by 4 by 4 by 4 hypercube. As three-dimensional beings, we can't actually see a 4D hypercube, but this is what it will look like projected into 3 space. What? Oh. Mm. But wait, what even is a line in 4 dimensions? Let's step back to 2 dimensions. Nice. Pick up a square and step in that direction. Yeah. You get a line when you keep taking that same step. We can write a line as x and y coordinates like 0, 0. We can represent the step as a vector like 0, 1, which tells us which direction we're going. To figure out the next point in the line, we just need to add the vector to our point. Because we are in two dimensions, there's three different directions we can step. And we can decide to step in either or both. In three dimensions, our step is the form of 0, 0, 1, 1, where each of these three lines can be a 0, a 1, or a 0. Like a 0, 0, 0, and other 0, and then. All dimensions is the same. Our steps are defined by pairs of the form 0, 1, 1, 0. We just take a four-dimensional point and let that step do it over and that creates our line. So representing a hypercube as a 3D projection, we can also represent it as 16 4x4s. Oh, sorry, oh, 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 oh. Infinite photos. Almost 2D and stay with me. Oh yeah, this is long. We can generalize the problem instead of looking for photos, we're looking for sequences of numbers. For example, we can replace f0 and that with the number 0, 1, 2, and a 3 q and search for sequence 0, 1, 2. The problem is the same. You're looking for a tree-length sequence in a three-dimensional cube. They generalize further and look for like sequences and then dimensional hypercubes. For example, imagine looking for a sequence 0, 1, 100 in a third dimensional hypercube. Um, what's the probability of finding a 0 to n sequence in an n dimensional hypercube at n tends to infinity? Unlike n, we might never expect to find such sequence. It needs to be exactly 0, 1, 2, and infinity. The odds of delta are 1 in infinity, the power of infinity. On the other hand, high-dimensional spaces are exponentially more connected, and there are so many more ways to control lines. It will be almost guaranteed some line here had that sequence. Let's solve how these two effects cancel out. If the increased priority of the sequence grew perfectly with the increased connectivity of higher dimensional spaces. Infinity. In a shocking conclusion, that's exactly what happened. The crowd the exact same rate and the probability converges to constant. In an infinite dimensional hypercube, you have a 99.832% chance of finding out this consequence. No matter how large the cube gets, the number stays the same. Now see the from those zero. Never mind. Conclusion. Now you're ready. I officially love you a professional falsifier. But how do you feel as in a bit? From an Nokia's research to a land of infinity. What a strange journey. Thanks for coming. Made with a lesser than 3 by John. Bye.